Okay, this is lesson 3.4, which is rate of change, and I'm going to record several videos for this lesson. This is part 1. If you remember, on lesson 2.1 we learned the formula for the average rate of change, and we used the change in y over the change in x, delta y over delta x, which is also f of x1 minus f of x initial minus x1 over x1 minus x initial. That was before we learned about limits, but now that we understand, we have all those concepts of derivatives and the limit, we can define the instantaneous rate of change. If you remember, the average rate of change, it was like the slope of a second line, and the instantaneous, it was the slope of a tangent line. That means that we can use the definition of the derivative, f prime of x initial, which is the limit when delta x tends to 0 of delta y over delta x, which is also the limit using the difference quotient when x1 tends to x initial of f of x1 minus f of x initial over x1 minus x initial. That means, if you remember that, if you recall that we are having several second lines that the limit of all these second lines are approaching the slope of the tangent line, which is on this other side. So in this case, this is the average rate of change, and in this case, this is the instantaneous rate of change. So if you remember, the second lines were approaching the slope of the tangent line. Okay, this was x initial and this was x1. So as x1 tends to x initial, and in this case, this is supposed to be x initial. Okay. Well, now that you understand this, we understand this concept, we just have to remember using Leibniz notation that if we have dy on dx, y will be the independent variable and x is the the other way around. X is the independent variable and y, it's my dependent variable. That means this, if we take that into consideration, we will see which are going to be the units, like degrees per minute, or it can be like degrees per kilometer, or kilometers per hour, whatever. Okay, let's go and let's start solving example number 1 about this lesson. On example number 1, I was trying to upload the table of values that we have there on page 129, but I was not able to insert images in this application. So I will ask you to open your books on page 129 and to take a look at the graph, at the table and the graph that we have there. This is a table that contains data on the temperature on the surface area of Mars at Martian time, and it was calculated by a NASA Pathfinder probe. Okay, and you have to calculate the average rate of change of the temperature from, so in letter A, average rate of change of the temperature between 6:11 a.m. and 9:05 a.m. So if you see the table of values, you have at 6:11, which is this is the time. The temperature at 6:11 was negative 71.6, and then you have several values here, and then you have the other value at 9:05. At 9:05, the temperature was negative 44.3. So if we have to calculate the average rate of change on that one, we will be doing the change in the temperature over the change in the time. So my delta T over capital T or big T over delta small t. Big T, temperature, small t, it's time. So in this case, the length between 6:11 and 9:05, it's 2 hours and 54 minutes, which is 2.9 hours in this case. And the change that we have in the temperature, I'm sorry, this is the time, so 2.9 is the time here. And the change in temperature, it was minus 44.3 minus negative 71.6, which this one 2.9 here, this is gonna be 27.3 over 2.9, which is approximately 9.4 degrees Celsius per hour. Okay, that's the answer of this first example. Now let's do letter B. You have to use figure 3 to estimate the rate of change at t. That was letter A, this is letter B. To estimate the rate of change at, okay, and we are estimating, we are using a table like the graph, rate of change at t, which equals 12:28 p.m. And we have a graph, something like that. I am sorry. We have a graph here, and we have something like that, and the line was, the point was here. So if I want to find the rate of change at a particular point, I need another point to have like the change in y over the change in x. So I will choose another point in this part, and with the 2 points I will get the values. So in this case it will be dt, d capital T or bt, big T over small d, small t, the change in temperature over the change in time, which is the slope of that tangent line. And the temperature, it was negative 22.3, reading more or less reading the graph, minus negative 51, all that over 7.67. I use the point A, which is at 448. That's what I use. And the temperature, it's gonna be, the slope, it's gonna be approximately 3.7 degrees Celsius per hour, which is the answer of letter B. Understood? Okay, let's go, and now let's solve example number 2. Let me clear this, and let's start with example number 2. On example number 2, which is also page 129, we have the equation A, which equals pi r squared, which is the known formula for the area of a circle of radius r. You have to compute in letter A, you have to compute dA, the change in the area with respect to the change of the radius when the radius equals 2. That means the instantaneous rate of change at r equals 2. And you also have to calculate dA on dr when r equals 5. Okay? So let's start. We need to find first the derivative. dA on dr equals, remember, the derivative of a constant times the derivative of a constant times a function will be the constant pi, the constant pi times the derivative of a function, the derivative of r squared, it's the exponent x to the n, it's going to be n, which is 2r. Okay, so this is going to be 2 pi r, and dA on dr when r equals 2 equals 2 pi times 2, which equals 4 pi, and dA on dr when the radius equals 5 equals 10 pi. Okay, just by looking at the numbers, this one it's gonna be bigger than the other one because we have 4 pi and 10 pi on the other side. Okay, then there's another question, letter B. Why is the radius, the instantaneous rate of change or the derivative larger at the radius r equals 5? If you take a look at page 130, you will see that if you have the radius of a small circle, and this is a change, and you have another, a bigger circle, even delta r, which is this part that it's here, the change in the radius, it's the same as the one that we have here, but the radius of this circle it's bigger than the one that it's here. So just by taking that into consideration, the radius, the change in the radius, and when the radius equals 5, it's bigger than the other one. And if you see the graph that we have here, it's something like this. If this is the equation, you have a curve like this, and then the slope, this is at point 2, I'm sorry, this is at 2, because I'm using a different pen, that's why. This is at 2 and this is at 5, and the slope at 2 it's like this, and the slope at 5 is like that. So just by looking at that graph, you can understand that the slope of the tangent line at 2 it's smaller or less steeper than the slope at r equals 5. Okay, this is the radius and this is the area. Okay, well, this is the first part of the lesson 3.4, which is rates of change.